Hi there, and welcome to video 6 of Module 4, Dangers of the Least Squares Regression Line. In this video, we'll explore two different ways that the least squares regression line can be misused, so hopefully we don't misuse it. Let's get started. As you'll recall, throughout all of the Module 4 videos, we're exploring some data that Harriet collected about the displacement volume and the combined city and highway gas mileage for several vehicles from 2017. So this is the data we're going to be making reference to as we work through some examples in this video. So we want to be careful not to misuse the least squares regression line when we are interpreting data. So here are two ways that the line is commonly misused. The first one is called extrapolation. Extrapolation happens when the least squares regression line is used to predict results outside the range of the data. So this would be something like I collect data from the 1950s to the 1970s, and then I try and use that data to make a prediction for today. That doesn't really make sense to do because those years are in the distant past now, and several things have changed since then. So you want to make sure that your predictions are around the time of when the data was found. So we've got an example, and it says determine whether it would be extrapolation to use Harriet's least squares regression line to make a prediction about a vehicle with a displacement volume of, and here we have three different situations, 4 liters, 8 liters, or 1.6 liters. So let's take a moment and look back at the data so that we can figure out whether these make sense. So here, when I look at the displacement volume values that were contained in the table, kind of doing a quick scan, the lowest number here is 1 liter, and the largest number is 5.7 liters. So that means it's going to be appropriate to make predictions for values that are within that range, or maybe just before. So if I have a vehicle with a displacement volume of 0.9 liters, or maybe a displacement volume of like 6 liters, maybe, that would be within acceptable parameters. But if it's outside of that, if it's outside of this 1 to 5.7 ratio, or fairly far away from that, then that would not be appropriate. So let's go back and look at what our options were. So our three options were 4 liters, 8 liters, and 1.6 liters. So the two options on the end, the 4 liters and the 1.6 liters, would be appropriate for us to make predictions about because those fall within that 1 to 5.7 liter range. The 8 liter value would probably be extrapolation because it's more distant from our range of values, so it would not be appropriate to make a prediction for 8 liters. Okay, so let's look at a second way that this line might be misused or how it should be used. So predictions should be used to compare currently existing conditions, not to predict future conditions. So what I mean by this is if we're looking at the vehicles from Harriet's data, we can compare two of the vehicles with established displacement volumes from 2017, but we should not use the least squares regression line to predict what would happen if I installed a new engine in the vehicle or if I made a new vehicle 10 years later, right? So I shouldn't be using it to predict something that happens in the future. So here's another example. Suppose that Freddie finds that the lengths of a person's legs in centimeters and their walking speed are positively correlated, and he finds this least squares regression line. We want to know which of the following is an appropriate interpretation of this. So if I look at this least squares regression line, I notice it has a y-intercept of 141 because that's the number that doesn't have the x beside it, and it has a slope of 0.30. So what this means is that two people who have leg lengths that are 1 centimeter apart are likely to have walking speeds that are 0.3 centimeters per second that are different. So let's look at our options. Option A says, my legs are 86 centimeters long. If I wear 1 centimeter heels, my walking speed will increase by 0.30 centimeters per second. This is kind of silly, as anyone who's worn heels knows. I mean, even if 1 centimeter is not that big, if you wear heels, you're probably not going to be walking much faster. So let's look at option B. April is 1 centimeter taller than June. So April will have a walking speed that is 0.30 centimeters per second faster than June's. Option B is the one that makes sense because it compares two currently existing conditions. We're not predicting what will happen as a result of changing something. Okay, so this example is going to combine some ideas from throughout Module 4 so far. So what I would recommend is that you actually pause the video here and try and work through these 3 examples on your own to kind of test your understanding. So these are 3 true-false problems. So take a moment to pause the video, work through them, and then you can unpause them to hear the explanation and see how you did. Okay, have you given it a shot? All right, let's work through it. So this says, suppose a teacher finds the least squares regression line for a number of absences, x, and a student's final grade in the class, y, to be y hat equals 85 minus 2.79x. Determine whether each statement below is true or false. Okay, so it looks like x, the independent variable, is the number of absences, and y is your grade in the class. So we're using absences to help find an estimate for a final grade. So part A says the y-intercept is an estimate that students who were never absent had a final grade of 85. In this case, remember that the y-intercept in the equation is the value that doesn't have the x beside it. So here, 85 is the number that doesn't have the x. So 85 is definitely the y-intercept. So that part is correct. The next part we have to check out is to see if what it's saying is true about the 85. So the y-intercept is the value you get when the x value is 0. Since x represents the number of absences, if x is 0, that would mean somebody had no absences, meaning they were never absent. So A is true. The y-intercept is an estimate that students who were never absent had a final grade of 85. Okay, let's look at part B. Being absent in this teacher's class will cause your grade to be lower. Oh my goodness, so there's a phrase in this sentence that should jump out at you as terrible, terrible, terrible. Do you see what it is? Will cause. So remember, most important thing that you can learn in a statistics class, one of them, is that correlation is not causation. Just because two things are correlated does not mean that it is cause and effect. There's no statement here that says the teacher has an attendance policy where absences cause your grades to decrease. Maybe this is just a relationship that the teacher's noticing because students who miss class miss information and assignments, and so their grade tends to be lower. So this one is definitely false. Whenever you see that phrase about being cause and effect, that should jump right out at you as like a red flag. That's a warning. This is not a true statement. Next, let's look at the last part. Part C, if a student reduces their number of absences by 3 days, their grade will be improved by 8.37 points. So first of all, I don't know how a student would reduce their absences by 3 days. Maybe they would go to office hours to make up the classes they missed, perhaps, but I don't know how you would like unbe absent. The other thing that statement C is saying to me is that we're trying to make a prediction if we change something about the x value. So we're saying if I change the x, that will result in a change in y. As we saw earlier in this video, that is a false thing. You can only use the least squares regression line to compare two students who have a different number of absences. You cannot say what's going to happen if you change a number of absences. So statement C is also false. All right, that concludes our video for dangers and warnings about the least squares regression line. In the next video, we'll be discussing the correlation coefficient and how you can find summary values for data. Thanks for watching. and have a great day.